up, guys? Today we are doing extractions and phase equilibria. How fun. So these are two super important concepts that are really necessary in many industries for enriching and isolating compounds. And it's normally used in like solvents to extract metals or separate certain analytes that we use, or like just to see if there's some impurities in our water many times. So what normally happens is you'll have a two-layered system of two immiscible liquids. So this would normally be organic, and this would normally be aqueous. All right, so this actually depends on the density of the two layers. So if the organic density is less than your aqueous density, then you know the aqueous density is going to be at the bottom, organic layer is going to be at the top. Okay, so first off, we have something that we call a partition coefficient. So basically what happens is you have two versions of the same compound, one in the organic phase and the other one in the aqueous phase. Now these two continually partition between the two phases, so they'll go up and down, right? And you're literally in an experiment, you're going to shake the thing and it will start to partition. So what the partition coefficient says is, it's a fancy K partition that says that the activity of your organic phase, I'm going to call it 1, and the activity of your organic phase 2. That's your partition coefficient. So this tells you how much is going into your organic phase and how much is going into your aqueous phase. But we normally, this is not common because activities very much differ for like each compound, and it's really hard to get the activities. So what we can do is we can simplify the partition coefficient to something a bit different. Okay, so we're back and we have our partition coefficient that tells us how much is going to our organic phase and how much is going to our aqueous phase. However, we said this is not common because activities are hard to get, all right? So instead of using this, we can actually simplify this to a partition coefficient, also a K, but not so fancy. That is basically just the concentration of our organic phase over the concentration of our aqueous phase, okay? But it is important to note that this is only a possible approximation in dilute systems, because when it gets concentrated, this theory starts to fail, because then we actually need the activities, because activities play a much bigger role in concentrated systems. However, in dilute systems, this is totally fine. We can use the concentration, and we love using the concentration. So this is the partition coefficient, and this basically tells us that if we have two phases, and I'm going to use color here to really emphasize my point. Here you go. Here you have your organic phase, right? And here you have your, let's use green, your aqueous phase. So the Kp, the partition coefficient, just tells you how much of your desired analyte, the thing you're trying to extract, is here and how much of it is here. So if the Kp, sorry, I'm going to use a red pen again. If Kp is large, like let's say, then we know the concentration of the organic solvent is a lot greater than the concentration of the aqueous solvent, which is what we want. Normally when we do extractions, we put our desired solvent or analyte in the aqueous phase and we extract it in the organic phase. That's just the easiest way to do it and the cheapest as well. So next thing, if we have Kp that's like let's say less than 1, sorry, this should be 1, okay? Then we know that, oh no, we've got a lot of aqueous concentration, which means we didn't extract a lot into the organic phase. And that's a problem, because that's actually where we get the extraction from most of the time. So recall this, Z organic and Z aqueous. So they keep on partitioning. The partition coefficient tells us how much partitioning is happening and where most of our analyte is going. Okay, so following from this is an important equation, important concept. But then we get our distribution constant. So when, let's say we have our organic phase and we have our aqueous phase, and let's say aqueous phases normally dissociates as follows, especially if it's an acid. And then we have our organic version, which just partitions between organic. So two things are happening here. We have Z organic is partitioning to Z aqueous. And in this case, it's not Z, but HA. So we'll have HA organic and HA aqueous. 1. And then we also have our, I'm going to use green to emphasize this, HA that dissociates into its conjugate base and acid, okay? So there you go, two reactions happening. And then instead of using our partition coefficient, we're going to use something a little bit similar, but not entirely. So we are going to use our distribution constant, which basically says that the total concentration of HA organic divided by the total concentration of HA aqueous. Okay, and in this case, and this is important, we would have HA in the organic phase. That's the only HA we have there. And then we have HA in the aqueous phase, but it also comes in this form, its conjugate base form. So that's the distribution constant, which basically symbolizes the same as the partition coefficient. There's a reason we call them two different things, because they start to vary as the pH varies. And I'll show you that now. But basically this tells the same. This says, well, if this is low concentration and this is high concentration, you have a big DC. If you have a big DC, you know a lot of your analyte is in your organic phase, and that's important. That's what we want. If, on the other hand, we have little concentration of our organic phase and high concentration of our aqueous phase, then we know our partitioning didn't work as planned and we don't have a lot of analyte in our organic phase for extraction. Okay, next up, we're going to derive some things. Okay, guys, now we have our distribution constant. Now I have to be careful, I want to write this, but DC, no, I'm going to say it right here. Okay. DC is equal to, well, we said the concentration of HA in the organic phase and HA in the aqueous phase, but also with its conjugate base, because we're considering the one where we have partitioning in the organic phase and we have an aqueous phase that can dissociate into these two, all right? Okay, so we are using this system for this case, right? And from this, it follows that we have two constants. We have our partitioning one, which just says this, right? It's really almost similar, but not quite. And then it follows from this that HA1 is equal to the KP. All this fits? I don't think so. This follows that HA1 in our organic phase, I'm going to write it on the outside, is this, right? I just multiplied this to the other side, okay? And from this, we leave it like this for now. And Ka is just the dissociation constant, right? And looks as follows, right? Now we can write HA2 as this, as basically just swapping the two around, okay? And then we can substitute this back into that, get the following bad boy, Kp over Ka, A minus H plus. Okay, so this is what HA is equal to, right? And, oh no, sorry, this is what HA1 is equal to. So HA1, our organic concentration. There you go. So we got an expression for both. Fine. Okay. Now it follows that this becomes HA1. We have a new way of writing it, which is cool, and it's important because this will give us a bit more insights about this distribution constant and why it differs from the Kp. And HA2 can be written as what we have here, plus A minus. Right. Now we take out spatial characters on both sides. Both sides have an A concentration over a Ka, right? Leaving us with Kp and the hydrogen concentration, which will become important now. This is all divided by the same concentration over Ka. And in this case, it becomes the hydrogen plus Ka. Okay, so now that we've used everything here, I can take this out. And this is what DC becomes. DC becomes Kp, the hydrogen concentration. I omitted the 2, but we know that we only have hydrogen concentration in the aqueous phase. But I'll put it back now for completeness sake. This is an important equation. All right, so if DC is equal to this, and we have a high concentration, we will get something, and if we have a low concentration, we will get something. So let's consider this next. Okay, so now something important. So we got a new way of writing our distribution constant, which is almost just dependent on this bad boy right here. Okay, now what I want you to consider are 2 cases. So when this concentration is really big, so great that it's a lot bigger than this, and the other one, the opposites. But first, let's look at this one. So in this case, basically what's going to happen is DC will approximately become Kp over H plus 2 over H plus 2, right? Because this is so big, it just overshadows the Ka. And they can just cancel. And here we have, oh, look at that. For high concentrations of hydrogen, the distribution constant is equal to the partitioning constant, which is awesome. And it graphically looks as follows. So you'll have log of DC over the pH, 1 to 14. And it will basically just be equal to a constant, Kp. What happens if it gets big, though? What happens here? Okay, because this is for high concentrations of hydrogen. And this is normally at low pH, right? So next up, we'll see what happens here. So when we have a hydrogen concentration, which is a lot smaller than Ka, then DC basically becomes Kp H bar 2 over Ka. Not so nice anymore. And basically what this is going to turn into, it will be log dC of a pH, low, high, right? So concentration of hydrogen is really low here, and the concentration of hydrogen is really high here. So it goes constant, 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 dips, okay? And what this basically will mean is that here, okay, it's fine, it's fine, it's fine. Organic phase is winning, and here, aqueous phase is winning. And because the DC value is becoming smaller and smaller. And we said that from our original equation of DC, whenever DC gets smaller, we know the concentration of our aqueous analyte is getting larger. So this is what this means, right? So because the DC is getting smaller, we know that the aqueous is winning. The aqueous solvent is winning the partitioning competition. And this is normally the ideal place where we want to be for organic solvents, for organic extractions. And yeah, next up, we will finish this with graphs. So yeah, I'll see you now.